Hello there, and welcome to the Sleepy Nature channel. Tonight, we are going to rest beneath a very special kind of magic, one that has been quietly happening above your head every time you have ever walked beneath a tree. Did you know that if you took a single branch from a tree and held it up in your hand, it would look almost exactly like the whole tree itself? That the smallest twig at the very tip of the highest branch echoes the same gentle shape as the entire trunk reaching for the sky. Trees do not grow by accident. They follow a pattern so ancient and so perfect that mathematicians gave it a name, fractals. And tonight, very softly, very slowly, we are going to wander through that pattern together, like two quiet people walking a forest path in the last golden light of the day. So let your shoulders drop. Let your breath come slow and easy. You do not need to hold anything tonight. Just let the world grow soft around you and follow the branches wherever they lead. Imagine you are standing at the edge of a forest just as the evening begins to breathe. The air is cool, but not cold. The kind of cool that feels like a soft cloth laid gently over your face. The light is the color of honey, coming in low and sideways through the trees, turning every leaf edge into a little golden wire. You're not going anywhere. You're simply standing and looking up. Above you, a tree spreads its arms across the sky. And if you let your eyes go soft, not squinting, just soft, you begin to notice something strange and wonderful. The way the trunk splits into two large branches. The way each of those branches splits again into two slightly smaller ones. And then again, and then again. Each split a quieter, gentler echo of the one before it. A pattern repeating itself into smaller and smaller whispers until it becomes the finest, most delicate tracery of twigs against the pale evening sky. This is a fractal. The word comes from the Latin word fractus, which means broken or fragmented. But there is nothing broken about what you are seeing. It is the most whole and complete thing imaginable. A pattern that contains itself over and over at every scale. A mathematician named Benoit Mandelbrot first gave fractals their name in 1975. He had been looking at coastlines, clouds, and yes, trees, and had noticed that nature seemed to love this trick of repetition at every scale. He called it self-similarity. The idea that a small piece of something, when you look closely enough, resembles the whole. But trees had known this long before any mathematician gave it a name. Trees have been practicing fractals for hundreds of millions of years, long before humans were here to notice or to wonder. The oldest tree-like plants on Earth appeared around 385 million years ago, and even their fossilized remains show this same branching, this same quiet repetition. Let your breath slow down a little. In through your nose, soft and easy. Out through your mouth, like you are breathing a little fog into the evening air. Good. Just like that. The branching of a tree is not random, even though it can look beautifully wild. Every tree follows an internal logic, a kind of architectural wisdom built into its cells. When a branch reaches a certain thickness, it knows it is time to split. When light comes from one direction, the new growth leans toward it. When wind pushes consistently from the west, the branches thicken on the windward side to hold steady. There is a rule that many trees follow called Leonardo's rule, named after Leonardo da Vinci, who first wrote it down in his notebooks around the year 1500. He noticed that if you added up the cross-sections of all the smaller branches at any given height of a tree, they equaled the cross-section of the trunk below them. The tree, in other words, perfectly conserves its own thickness as it divides. No wood is wasted. No pathway for water is too wide or too narrow. Da Vinci drew trees the way other people breathed, naturally, easily, because he understood that a tree was not just a shape. It was a system, a living architecture. Scientists studying this rule centuries later confirmed that Da Vinci was right. And more than that, they found that this rule helps trees resist wind. When the tree divides evenly according to this principle, the stress of a gust of wind is spread out across all the branches equally, like water finding its way through many small streams instead of one great flood. The tree flexes and bends, and nothing breaks. Think of that. A tree is flexible not despite its fractal branching, but because of it. Its very shape is a kind of wisdom, a kind of softness built out of wood. The branching angle, the angle at which one branch separates from another, also follows patterns. In many trees, this angle hovers around the golden angle, approximately 137.5 degrees, which is related to the golden ratio. This is the same ratio you find in the spiraling of a nautilus shell, the seeds of a sunflower, the unfurling of a fern. Nature returns to this number the way water returns to the sea, because it works, because it is efficient, because it fills space beautifully without gaps and without overcrowding. Right now, if you look at any tree and trace two branches that split from the same point, you might notice they do not simply go straight out from each other. They curve gently, they reach. One branch leans a little toward the light. One stays a little lower to gather what drifts through the canopy below. They are not competing. They are sharing. The reason trees branch at all, rather than simply growing taller and taller as a single trunk, comes down to light. Sunlight is the food that every leaf makes for the tree, and a single straight column of wood with leaves only at the very top would waste all the space to the sides. By branching, a tree spreads its leaves out in 3 dimensions, catching light from many angles, filling the air around it with green, photosynthesizing surfaces like a vast, gentle net cast across the sky. Studies have shown that the fractal branching of trees allows them to pack an extraordinary amount of leaf surface into a relatively small volume of space. A single large oak tree can have around 200,000 leaves. If you spread all those leaves out flat, they would cover an area roughly the size of a tennis court. But the tree holds them all in the volume of its canopy, like a gentle green cloud, each leaf tilted just so. And this brings us to something very quiet and very beautiful. The leaves are also fractals, the veins of a single leaf branch in exactly the same way as the tree branches above you. The main vein runs up the center of the leaf like a spine, and from it smaller veins branch off, and from those smaller still, until the smallest veins form an almost invisible net of pathways, carrying water and sugars to every green cell. So when you look at a leaf, you're also looking at the tree. And when you look at the tree, you're looking at the leaf. The same story, told at different sizes, the same song, sung in different octaves. Let your eyes close for just a moment, if they want to. Let the image of those branching veins rest softly behind your eyelids. A map of pathways, going smaller and smaller, quieter and quieter, until they become something too fine to see, only to feel. The tree is breathing tonight too, quietly, through tiny openings in its leaves called stomata, small mouths essentially, that open in the day to take in carbon dioxide and release oxygen, and close at night like someone drifting to sleep. Right now, in the dark, the tree and you are doing something similar, resting, conserving, dreaming in your own quiet ways. If you are enjoying this gentle drift through the forest, feel free to leave a comment below. We would love to know what kind of tree you imagine when you close your eyes. And if you have not already, a like on this video helps more sleepy wanderers find their way here. The roots of a tree are also fractal, mirroring the branches above the ground. They too split and divide, reaching into the soil in the same pattern of decreasing repetition. Large roots becoming medium roots, becoming fine roots, becoming root hairs so small they are barely wider than a single cell. These root hairs are where the real drinking happens, where water moves from the cool, dark soil into the living wood of the tree, beginning the long, quiet journey upward to the leaves. A fully grown tree might have hundreds of miles of roots beneath it, not one great taproot plunging down like a spike, but a vast, spreading network, branching and branching again, hugging the soil like 10,000 gentle fingers. Some of those root tips are exploring soil that no root has ever touched before, feeling their way through the dark, patient, and unhurried. The tree is patient. It does not hurry. It simply keeps branching, keeps reaching, keeps repeating the one pattern it knows. The pattern that works, the pattern that has always worked, the pattern it inherited from every tree that came before it, stretching back hundreds of millions of years into a past so deep it becomes something like a dream. And you, too, are branching. Your lungs branch. Your blood vessels branch. Your nervous system sends its signals through branching pathways that look, under a microscope, remarkably like the silhouette of a winter tree against a white sky. You are not so different from the thing you are resting beneath. You are both expressions of the same patient mathematics, the same ancient language the universe learned to speak long before either of you existed. The evening is deepening now. The honey gold light is fading from the treetops, settling into something softer, a lavender gray that makes the branches look like they are drawn in pencil on pale paper. You are still beneath the tree, and you are still looking up, but now you are beginning to see not just the shape of the tree, but the space between its branches, the sky, broken into 1,000 irregular pieces by the pattern of the wood, like a stained glass window made by no one, assembled over decades by light and growth and weather. There is a name for this too. Scientists call it the fractal dimension of a tree's canopy, a measure of how completely the branches fill the space around them. A perfectly solid object, like a cube, has a dimension of 3. A flat surface has a dimension of 2, but a tree's canopy sits somewhere in between, complex enough to be more than flat, but open enough to let light and wind move through. Most trees have a canopy fractal dimension of between 1.5 and 2.5. That strange in-between number is part of what makes them beautiful. They are neither too dense nor too spare. They are exactly as open as they need to be. Researchers studying human responses to fractal patterns have found something quietly wonderful. People feel more relaxed when they look at fractals. Not just tree fractals, any fractal. The branching of rivers, the edges of clouds, the texture of a rocky shore. Our nervous systems seem to recognize these patterns as safe, as natural, as home. Your body knows what your mind may have forgotten, that this branching, repeating world is the world you come from, and it is a good world. There is a researcher named Richard Taylor who has spent years studying this effect. He found that looking at fractal images with the right level of complexity, not too simple, not too chaotic, can reduce physiological stress by as much as 60%. He has called this the fractal fluency of the human eye, the idea that our visual system evolved in a fractal world and is most at ease in one. Your eyes evolved looking at trees. They're very good at this. Let them rest in what they know. Different species of trees have different fractal signatures, not just in their overall shape, but in the precise angles and proportions of their branching. A weeping willow branches very differently from a cedar of Lebanon. An aspen's crown is fine and quivering, its thousands of small leaves on flattened stems turning and flashing in the breeze. An old apple tree is gnarled and asymmetric, its branches thickened by years of fruit. Each is a fractal, but each is a different accent, a different dialect of the same language. Scientists can now identify tree species from photographs of their branching patterns alone, without leaves, without bark, without fruit. The silhouette of a bare winter tree carries its identity in its geometry, its fractal fingerprint. A young tree branches more freely, more experimentally. It is still finding its shape, still responding to the particular light and wind and soil of its particular place. As it ages, its branching becomes more set, more characteristic, a settled handwriting. The oldest trees have the most complex fractals of all, their shapes bearing the record of every storm and drought and abundant spring they have ever lived through. There is a tree in Sweden called Old Giko, a Norway spruce, whose root system is thought to be around 9,500 years old. The trunk you see is only a few hundred years old, but the root system beneath it has been branching and branching, sending up new trunks as old ones fell for nearly 10,000 years. It was already old when the pyramids were being built. It was already ancient when the alphabet was invented. And its roots, underground and out of sight, still follow the same fractal pattern they always have. Still dividing, still reaching, still quiet. Let that settle over you like a blanket. 9,500 years of branching, of patience, of simply growing in the pattern that was given without hurry, without doubt. In the spring, a tree's branches become visible in a new way, not by their wood, but by their blossoms. Cherry trees are fractal in bloom. The small clusters of flowers at the tip of each twig, multiplied across thousands of twigs, create a cloud of pink that seems to float. You are not seeing individual flowers when you look at a flowering cherry from a distance. You are seeing a fractal bloom, the sum of thousands of small echoes adding up to something larger than any one of them could be alone. In autumn, this becomes true again, in a different key. Each leaf changing color creates a fractal pattern of red and gold and orange across the canopy, because the leaves at the tips of branches, farthest from the tree's main water supply, change first. The color moves inward, from the outermost edges of the fractal to its center, like a tide coming in very slowly, very gently, from all sides at once. The process of color change itself is fractal in time. It does not happen all at once. It happens gradually, leaf by leaf, twig by twig, spreading across the tree in the same pattern by which the tree was built. From the extremities inward, from the smallest to the largest, following the branching pathway home. You might like to check out our playlist of sleepy nature stories. There are many quiet forests waiting for you there whenever you need them. The way water moves through a tree is also fractal in its logic. Water enters at the root tips, moves upward through the branching root system, enters the trunk, and then travels upward through the xylem, the tree's internal plumbing, which also branches in fractal patterns from the wide main vessels in the trunk to narrower ones in the large branches to narrower still in the smaller branches, until finally it arrives at the leaves. There, some of it is used for photosynthesis, and the rest evaporates from the stomata into the air. Transpiration, it is called. A single large tree can transpire hundreds of liters of water on a warm summer day, breathing out moisture the way you breathe out the faintest mist of warmth. This evaporated water joins the air above the forest. Over large forests, enough water is transpired to actually influence local rainfall patterns. The Amazon rainforest creates what scientists call flying rivers, enormous aerial pathways of moisture that travel hundreds of miles and eventually fall as rain far from where they began. The fractal branching of millions of trees creates, in aggregate, a kind of circulatory system for an entire continent. The branching pattern of rivers seen from above also looks like a tree, or a tree looks like a river, depending on which direction you travel. Both are doing the same thing, moving something, water, nutrients, light, from many small sources to one large outlet, or from one large source to many small destinations. The logic is the same. The pattern is the same. The universe, it seems, has one very good idea and uses it everywhere. When lightning strikes, it branches in fractals. The discharge of electricity finds the most efficient path through the air, and as it moves, it forks and forks again, a brilliant, instantaneous tree of light. It is gone before you can really see it, but if you photograph it and slow it down, you find the same pattern, the same self-similar branching, the same decreasing repetition from thick to fine, from one to many. Sometimes lightning strikes a tree, and the current travels down through the tree's own branching structure, water-filled channels that conduct electricity. And if the tree survives, it sometimes bears a pattern on its bark. A Lichtenberg figure, a fern-shaped scar that mirrors the path the lightning took, a fractal pressed into wood by a fractal of light, the tree wearing the sky's pattern on its own skin. Breathe in softly and out. The branches above you are still there, still tracing their patient pattern against the darkening sky. Stars are beginning to appear in the spaces between the twigs, tiny points of light framed by tiny frames of wood. The world is layering itself into quiet. Somewhere behind you, there is a sound you have been half hearing without noticing, the sound of water moving slowly over stones. A small stream nearby, threading its way through the roots at the edge of the forest. Its sound is like a conversation that has been going on for a long time between the water and the stone, and neither one is in a hurry to finish. The stream is, in its way, a tree turned sideways, or perhaps the tree is a stream turned upward. Both begin at many small sources and gather toward one large flow. The stream begins as raindrops landing on leaves, the outermost tips of the canopy's fractal, and those drops run down the leaves to the twigs, and from the twigs to the branches, and from the branches to the trunk, and from the trunk to the roots, and from the roots into the soil, and through the soil to the stream. The rain becomes the stream by following the tree's own shape downward. This is called stem flow and through fall. A tree catches rain on its leaves and channels it, using its own fractal architecture toward its roots, essentially watering itself. A single large beech tree can redirect hundreds of liters of rainfall directly to its own root zone during a heavy rain. It is a rain catcher, a water director, a living watershed. The bark of a tree is also a kind of fractal surface. If you get close enough, really close, nose almost touching the bark of an old oak or a deeply furrowed pine, you see that the furrows and ridges repeat themselves at smaller and smaller scales. The deep grooves contain smaller grooves. The ridges have ridges on them. This rough, complex surface provides homes for hundreds of species, mosses and lichens and tiny insects and spiders. And the rougher the fractal texture of the bark, the more surface area it provides, and the more life it can hold. Some old trees have bark so deeply furrowed that the surface area of their bark exceeds the surface area of all their leaves combined. They are enormous living structures of texture, holding the moisture and warmth needed by countless small, soft creatures who live their whole lives in those crevices, never needing to go anywhere else. Let yourself imagine being very small, smaller than a fingernail, say, resting in a crevice of bark. Above you, the ridges of the bark rise like cliffs. Around you, the air is still and slightly damp, smelling of wood and moss and the faint sweetness of sap. You are completely sheltered. The world outside the crevice goes on, doing its windy, changeable things. But in here, everything is quiet. Everything is still. This is what a tree offers to thousands of creatures, the gift of shelter inside a fractal. The complexity of the tree's surface, its bark, its branches, the angles of its twigs, creates an enormous number of different microhabitats. A spot that is sunny in the morning and shaded in the afternoon, a hollow where water collects, a patch of soft moss on the north side of a branch, a tight fork where a bird can wedge its nest. A single mature oak tree can support more than 2,300 species of insects, birds, mammals, lichens, fungi, and plants. More than 2,300 species, a whole world held within one fractal. That number does not include the soil organisms in the root zone, which might add thousands more. The tree is not just a tree. It is a city, a continent, a world that built itself from one repeating pattern. The lichen on the bark is itself a fractal organism, a partnership between a fungus and an alga that grows in thin, irregular layers, branching and spreading across the bark surface in patterns that echo, very faintly, the branching of the tree itself. Lichens are among the slowest growing organisms on Earth. Some grow only a millimeter a year. They have been growing on this particular piece of bark for decades, perhaps centuries. They are in no hurry. They are simply being. Lichen can survive extraordinary conditions, extreme cold, drought, ultraviolet radiation at high altitudes. Some species have been put in vacuum chambers and exposed to the conditions of outer space and survived. They are ancient things. The oldest known lichen found in amber is around 400 million years old, which means lichens were colonizing tree surfaces before trees had developed their modern branching architecture. The lichen was there first, patiently spreading across whatever surface was available, waiting for the trees to arrive. Moss, too, grows on the bark and branches of trees, particularly on the shaded, moisture-retaining north sides of trunks in the northern hemisphere. Moss does not have roots. It absorbs water and nutrients directly through its leaves. It is a small, soft carpet laid over whatever hard surface will have it, and under a hand lens, each individual moss plant is a tiny, exquisitely branching structure. A fractal, again, at the scale of something barely visible. If you have been listening for a while and feel your eyes growing heavy, that is exactly right. Let them be heavy. There is nothing you need to see clearly right now. The branches will still be there when you open your eyes. The moss will still be soft. The stream will still be talking to the stones. The fungi that live in the soil beneath the tree also branch in fractals. Their mycelium, the underground network of fungal threads, spreads through the soil in exactly the same branching, self-similar pattern as the tree's roots above them. And here is perhaps the most wonderful thing. The tree's roots and the fungal mycelium are connected. They have formed a partnership called a mycorrhizal network, in which the fungus provides the tree with water and minerals from deep in the soil, and the tree provides the fungus with sugars made in the leaves. They are feeding each other, trading, caring for each other in the quiet language of chemistry and touch. These networks extend beyond a single tree. A mycorrhizal network in a forest can connect dozens, sometimes hundreds of trees, linking them underground in a web of fractal threads that allows nutrients and even chemical signals to pass between trees that may be separated by many meters of forest floor. Scientists have called this the wood wide web. It is real, and it is happening right now beneath the feet of every forest. Through these networks, larger trees have been observed sending extra sugars to smaller, younger trees growing in deep shade, trees that cannot yet photosynthesize enough to sustain themselves. The older trees do not do this consciously, of course. But the network does it. The branching fractal system of fungal threads distributes resources where they are needed, the way a bloodstream distributes oxygen to a cold hand. We would love to hear from you. Drop a comment with the name of your favorite tree or the forest you dream about. Reading your comments is one of our favorite things. The same network also carries warning signals. When one tree is attacked by insects or disease, it can release chemical compounds through its roots into the mycorrhizal network, and neighboring trees pick up these signals and begin producing their own defensive chemicals, tannins, and other compounds that make their leaves less palatable to insects, even before the attack reaches them. The forest warns itself. It has a kind of immune system that is also a community. All of this, the shared sugars, the warning signals, the water transport, the shelter for 1,000 species, all of it flows through fractal networks. The branching pattern is not merely the tree's shape. It is the tree's language, its circulatory system, its nervous system, its social network. Everything the tree does, it does through branching. You breathe out. The night air is cool and smells of earth and bark and the faint, clean scent of moving water. The stream is still there behind you. The tree is still above you. And somewhere below you, without making any sound at all, the network spreads through the dark soil, patient and alive. The night has fully arrived now. The sky between the branches is a deep blue black, and the stars that were shy at dusk are now fully present. Little fires in the immensity, held in the framework of the tree's outermost twigs, like a collection of small, brilliant seeds. The moon, somewhere to the south, casts a soft silver light across the topmost leaves, and from where you are, looking up, the tree seems to glow very faintly from within, as if it has been sipping the moonlight and is just now beginning to release it. Trees do not sleep the way we do, but they do have rhythms, internal biological clocks that respond to the length of the day and the temperature of the air, telling the tree when to flush with new growth in spring, when to slow its processes in autumn, when to drop its leaves. These rhythms are called circadian, from the Latin for about a day, and trees follow them with the same deep fidelity as any other living thing. At night, a tree's branches actually sag, very slightly. This was discovered by scientists using laser scanners to measure the exact position of branches on birch trees through the night and into the morning. As the tree stops transporting water upward, the pressure that helps support the branches, they droop a little, sometimes by as much as 10 centimeters at the branch tips. In the morning, as the sun rises and transpiration begins again, they lift back to their daytime position. The tree, in its slow way, is breathing out and in, drooping and lifting. Something very like sleeping and waking. Think of that. The branches above you are very slightly lowered right now, in the dark. They have let themselves come down a little, like shoulders relaxing at the end of a long day, like the chest slowing its breath toward sleep. The tree's annual growth rings are also a kind of fractal. Each ring is a record of 1 year's growth, wider in good years and narrower in drought years, and the pattern of wide and narrow rings repeats across centuries, encoding the memory of the weather in the geometry of the wood. A cross-section of a very old tree is like a page from the world's own diary. Scientists called dendrochronologists read these rings the way you might read a book, slowly, carefully, learning the tree's story from the patterns it left in its own wood. The oldest tree rings ever found belong to a bristlecone pine in California called Methuselah, which is around 4,850 years old. It was already growing when the first pharaohs ruled Egypt. Its rings hold the memory of thousands of winters and thousands of summers, droughts and floods and cold snaps and warm spells, each season pressed into the wood in its own thin layer, preserved and patient. The wood of a tree is not uniform. The inner wood, the heartwood, is dense and dark and no longer carries water. It is dead in a functional sense, though it still serves as the tree's structural skeleton. The outer wood, the sapwood, is lighter and alive, and this is where the water travels, in the fractal network of vessels that carries moisture from root to leaf. The boundary between heartwood and sapwood is not a sharp line, but a gradual transition, a slow darkening that moves inward over years as the tree builds more heartwood and expands outward. The grain of the wood, the patterns you see when you look at a cut piece of timber, are the growth rings viewed at an angle. When the cut is straight across the trunk, you see concentric circles. When the cut is at a slight angle, you see long oval patterns. When the cut is along the length of the trunk, you see the thin parallel lines of individual growth rings flowing around knots where old branch bases are embedded in the wood. Each knot is the base of a branch, the place where the fractal branching of the tree began to express itself outward from the trunk. A knot in a wooden plank is a cross-section through a branch base. The wood grain flows around it because the tree had to grow around the branch attachment, weaving the wood fibers of the trunk and the branch together in a complex interlocking pattern that makes the join extremely strong. It is, in its small way, a beautiful thing, a place where the tree's fractal structure was interrupted and then resumed, leaving its mark forever in the wood. Some trees have wood with extraordinary patterns: the curly maple, the bird's eye maple, the figured walnut. These patterns arise from subtle irregularities in the branching of the wood fibers, slight waviness or dimpling that catches light differently as you tilt the wood. No two pieces are the same. They are fractals shaped by a combination of genetic predisposition and the particular stresses the tree experienced, the way the wind pushed, the way the ground settled, the way the light fell, all recorded in the grain. Woodworkers who spend their lives working with these materials speak of the grain with a reverence that is almost like speaking of a landscape. They learn to read it before they cut, to understand which direction the fibers run, to work with the pattern rather than against it. It is a partnership, a conversation between the human hand and the tree's own long fractal history. If you feel called to, leave a like on this video. It is a small thing, but it means a great deal and helps us keep making these quiet stories. The cellulose fibers that make up wood are themselves structured at the molecular level in helical patterns, tiny spirals wound around tiny spirals. These molecular architectures give wood its strength, allowing it to bear extraordinary weight relative to its mass. A wood fiber is, pound for pound, stronger than steel in tension. The tree achieves this not with metal, but with biology. With the same patient, fractal logic, it applies to everything. Engineers and architects have been inspired by these structures for centuries. The vaulted ceilings of Gothic cathedrals echo the branching of trees, the ribs of the vault spreading outward from columns like the branches of stone trees, distributing the weight of the roof across many pathways, the same way a tree distributes the weight of wind and snow across its fractal structure. The builders of those cathedrals had not heard the word fractal, but they had looked at trees. Modern engineering still returns to the tree for inspiration. The design of heat sinks for electronics, the layout of ventilation systems in buildings, the structure of lightweight but strong components in aerospace, all increasingly draw on fractal branching patterns derived from biological models. Trees solved these problems long before we identified them as problems. The tree is, among everything else it is, an engineering manual written in wood. But tonight, you're not an engineer. Tonight, you're a person resting beneath a tree in the dark, listening to a stream and looking up at a branching pattern that is also a map of your own lungs and your own blood vessels and the rivers of the world and the paths that lightning takes. You are part of a very large family of branching things, and that family is ancient and quiet and does not need you to do anything right now except rest. So, rest. A soft wind has found its way into the forest. It comes from somewhere beyond the trees, from an open field perhaps, or from the direction of the sea, and it moves through the canopy above you with a sound like distant applause, or like the turning of many soft pages. The leaves rustle and settle, rustle and settle. The branches sway very gently, and in that swaying, the fractal geometry of the tree becomes visible in a new way, as movement, as wave, as rhythm. The way a tree moves in wind is itself fractal. The largest branches swing in long, slow arcs. The smaller branches move more quickly in shorter arcs. The twigs flutter fastest of all, and the leaves, the very tips of the fractal, shiver and turn and catch the moonlight. Each scale of the tree oscillates at its own frequency, and the sum of all those frequencies is the sound you hear, a complex, layered rustling that is never quite the same from one moment to the next, but always recognizably itself. This is one of the reasons the sound of wind in trees is so soothing. It contains a natural complexity, many different frequencies layered together, that our nervous systems recognize as safe background noise. Not like traffic, which has an irregular mechanical harshness. Not like music, which demands some attention. Just the layered fractal sound of a living thing moving in air. Different trees make different sounds in the wind. A poplar, with its flattened leaf stems, makes a high, whispering rattle. A pine makes a deep, sighing rush as the wind moves through its long needles. An oak makes a heavier, more measured sound. Its leaves are stiffer, its branches thicker, its movement slower. A bamboo grove makes a clicking, hollow sound because its hollow stems knock gently against each other as they sway. Leaves are shaped in part to manage wind. Leaves with deeply cut margins, like an oak leaf or a maple leaf, create less wind resistance than smooth, uncut leaves. The cuts allow the leaf to flex and deform in a gust, reducing the force the leaf transmits to the twig. A lobed leaf is a leaf that has found a compromise between maximum surface area for photosynthesis and minimum vulnerability to damage in a storm. The shape of the leaf is a negotiation between light and wind. The margin of a maple leaf, the serrated edge, is also in its way a fractal. The large lobes contain smaller sublobes, and the edges of those sublobes are serrated in turn. Not infinitely so. At some point, the complexity reaches the scale of individual cells and stops. But for several levels of magnification, you see the same cutting, dividing, repeating edge. The veins of a leaf, too, manage the mechanical stress of wind. When a gust pushes on a flat leaf, the force is transmitted to the veins, which distribute it along their branching network to the stem. A well-designed leaf vein network is one in which no single vein has to bear too much force, in which the load is shared across many pathways, the same logic as the tree's own branching. The leaf is a miniature tree, and it handles wind using the same principles its parent structure uses. There is a kind of tree, the trembling aspen, that seems designed for wind, or perhaps for the pleasure of watching wind. The aspen leaf's stem is flattened at right angles to the blade of the leaf, so that even a very light breeze causes the leaf to tremble and flash. A grove of aspens and a light wind looks like a river of green light. Millions of leaf faces tilting and turning, each one catching and reflecting differently, so that the whole grove seems to shimmer from within. It is one of the most beautiful sights in any temperate forest. An aspen grove is often a single organism. The individual trunks you see are not separate trees, but stems growing from one connected root system. A clone that may cover many acres and has been growing from a single original tree for thousands of years. One famous aspen grove in Utah, called Pando, is considered one of the largest and oldest living organisms on Earth. Its root system may be 80,000 years old. Its 40,000 individual trunks are all connected underground, all sharing the same fractal root network, all genetically identical, all shimmering together in the wind as one. The wind has quieted a little now. The rustling above you has softened. A few leaves are still turning, finding a slower rhythm. You breathe in the scent that a forest exhales at night. Damp earth, green wood, the faint sweetness of something flowering somewhere in the dark. This scent has a name: petrichor for the rain on earth smell, and phytoncides for the oils that trees release into the air, the same compounds that give a forest its clean, particular freshness. Phytoncides are released by trees as part of their immune system. They inhibit bacterial and fungal growth around the tree. But when humans breathe them in, something happens in the body. Stress hormones decrease, natural killer cell activity increases, blood pressure tends to lower. This effect has been studied in Japan, where the practice of Shinrin-yoku, forest bathing, has become an accepted component of health and well-being. The forest is healing, not metaphorically, but measurably, on a cellular level. You are, right now, even in imagination, doing something good for yourself. The fractal patterns above you and the phytoncide-scented air around you are both working in their quiet ways toward your ease. The bark of conifer trees, pines, firs, spruces, releases these compounds particularly richly. A walk through a pine forest has a different chemical atmosphere than a walk through a deciduous woodland. The pine's chemistry is sharper, cleaner, more medicinal. It has always been associated with clarity and health, which is why pine-scented products have such a long history of being connected with cleanliness and comfort. The association is not arbitrary. The pine has been offering this gift for millions of years. The resin that pines produce, the sticky, amber-colored substance that wells up through cracks in the bark, is also a defense and a healer. When the bark is damaged, resin flows to the wound and seals it, preventing infection. Insects trapped in resin can be preserved for millions of years. We find them in amber, perfectly preserved, the same way the tree preserved them, frozen in a moment of golden stillness. There is something beautiful about the idea that the tree's own defense system, working the way it always has given us windows into ancient worlds. The preserved insects and spiders and plant fragments in amber, each one a message from a forest that existed millions of years ago, when the continents were in different places and the birds had not yet learned to sing. The wind has stilled now. The forest is very quiet. You can hear, if you listen carefully, the very faint sound of dew forming. Not a sound exactly, more of an absence of sound, a deepening quiet that comes as the moisture in the air begins to settle on every leaf surface, every blade of grass, every strand of spider silk. The world is condensing itself toward dawn, very slowly, adding weight to the tips of the leaves, drop by drop. In the deep quiet of the forest at night, the birds are sleeping. Tucked into hollows and crannies and the dense middles of shrubs, each bird has found a place in the tree's fractal that suits it perfectly. A pocket of warmth and stillness in a world of branches. A small bird, a wren perhaps, has settled into a deep hollow in an old oak. Its feathers fluffed out against the night air, its tiny heartbeat steady and slow. It arrived here by flying, by following the tree's structure downward through the canopy, from the open air above the crown, through the large branches, through the smaller ones, into the particular quiet of this hollow. A bird's nest is built at a fork in the branches, at one of those branching points where the fractal of the tree provides a natural cradle. The bird does not choose this location by accident. It tests many forks with its body, pressing down, feeling the stability, sensing the angle. The nest is built to match the particular geometry of the particular fork, woven into the angles of that specific branching, a home shaped by and for the tree's own mathematics. Nesting material itself is often fractal. The base of a nest is typically made of thick twigs and sticks. The inner layers use progressively finer materials, smaller twigs, grass stems, plant fibers, hair, feathers. The finest layer of all, the cup that holds the eggs, is often lined with the softest available material: down, moss, spider silk, plant wool. The nest mirrors the tree's own architecture: large structures at the outside, progressively finer ones toward the center, a fractal of comfort. The spider silk used in some nests is one of the most remarkable materials in nature. Stronger than steel by weight, more elastic than nylon, and capable of stretching significantly before breaking. It is produced in the spider's own body from protein chains that the spider assembles into fibers as it spins. Each strand is thinner than a human hair, but a web made of many strands, arranged in their own fractal geometry of radial threads and spiral threads, is strong enough to stop a flying insect and elastic enough to absorb the impact without breaking. A spider web, viewed from the right angle in the right light, is a fractal of extraordinary delicacy. The radial threads go outward from the center like spokes, and the spiral threads wrap around and around, getting more densely packed toward the outside, where prey is most likely to be caught. Morning dew collects on each thread in a line of tiny drops, equally spaced, turning the web into a necklace of water beads, a fractal adorned with fractals, each drop a tiny lens reflecting a distorted image of the world. We are drifting now deeper into the quiet. If you find yourself at the edge of sleep, that is perfectly right. Let the stories continue to arrive softly, like leaves settling onto still water, and if sleep takes you before the end, that is a gift. These words will be here whenever you need them. The flight paths of birds through a forest could also follow fractal logic. A small bird moving through dense woodland does not fly in straight lines. It moves from branch to branch, its path curving and turning and backtracking, exploring the available space in a pattern that, if you traced it, would look remarkably like the branches of the tree itself. A fractal path through a fractal structure. The bird, in navigating its home, recapitulates the shape of the home. Insects that live in trees also move in fractal patterns, particularly when searching for food. A bark beetle exploring a tree trunk, a caterpillar moving through a canopy, an aphid walking from twig to twig. Each traces a path that is neither random nor straight, but somewhere between, a self-similar pattern of exploration that covers the available surface efficiently, returning sometimes to places already visited, moving outward in progressively larger sweeps. Ants, too. Ants foraging from a colony trace fractal paths across the forest floor, and the pheromone trails they leave, which other ants follow and reinforce, gradually crystallize from the fractal chaos of exploration into efficient, direct routes between the nest and good food sources. The efficient route is discovered by the fractal exploration. The fractal finds the line. The root systems of trees, as we have touched on before, also guide the exploration of soil by other organisms. Earthworms, soil mites, nematodes, bacteria, all move through the soil along pathways that were partly opened by the fractal network of roots. The roots do not just drink water, they create a geography, a landscape of tunnels and surfaces and chemical gradients that entire communities of organisms navigate by. An earthworm moving through the soil around a tree's roots has a body built on its own kind of fractal. Its digestive system branches internally, and the fine hairs on its skin increase its surface area in the same way that fractal textures do, maximizing the area available for gas exchange. The earthworm and the tree and the lichen and the spider are all expressions of the same underlying principle. More surface in less space, more function in simpler form. The moon, which has been moving slowly across the gap in the canopy above you, casts a shadow of the branches across the ground. That shadow is also a fractal, the large branches casting wide, dark shadows, the smaller branches casting narrower ones, the twigs casting hairlines of darkness, and the leaves casting their own layered shadows on top of all the rest. The moonlight breaks through in irregular patches, pools of silver on the forest floor, each one bordered by the soft dark of fractally overlapping shadows. These pools of light on a forest floor are called sunflecks in the daytime, and moonflecks by some poets at night. They move very slowly as the earth turns, each one sliding across the ground in a long arc, touching briefly on a patch of moss, then a stone, then a root, then moving on. If you watched all night, you would see the entire forest floor swept by this slow-moving light, illuminated patch by patch. Small plants on the forest floor have evolved specifically to take advantage of sunflecks. They have low light compensation points, meaning they can photosynthesize at very low light levels, but they can also briefly ramp up their photosynthesis when a sunfleck crosses them, taking advantage of that few minutes or seconds of brighter light before the shadow returns. They are patient opportunists, these shade plants. They do not need much. They use what comes. There is wisdom in that, in being suited to what is given, rather than needing more than the situation offers. The wood sorrel on the forest floor, with its clover-like leaves and tiny white flowers, does not complain about the shade. It has become very good at the shade. It has made the shade into a home. The night is at its deepest now, that hour when even the wind has found somewhere to rest, and the forest holds a stillness so complete that you can hear the silence as a kind of sound, a soft, full nothing that is somehow richer than any noise. The tree above you has stilled. The branches are barely moving. The dew has settled, and each twig is beaded with tiny drops that catch what little light exists and hold it. In this deepest quiet, let us follow the fractal pattern into the very smallest scales, into the cells of the tree itself. A tree cell, seen under a microscope, is its own architecture, a box-like shape with walls made of cellulose fibers arranged in a spiral pattern, giving the cell both strength and flexibility. Groups of cells form tubes, the xylem and phloem, which form vessels, which form branches, which form the tree. The fractal builds from cells to canopy, from a pattern too small to see to one large enough to shade an entire meadow. Inside each cell, the chloroplasts, the small green bodies where photosynthesis takes place, have their own internal membranes folded into stacked layers called thylakoids. These stacks are arranged in a pattern within the chloroplast, and the chloroplasts are arranged in a pattern within the cell, and the cells are arranged in the layer of the leaf, and the leaves are arranged on the twig, and the twigs on the branch. Layer upon layer upon layer of organization, each one echoing the others, all the way from the molecular to the magnificent. Photosynthesis itself is a kind of fractal process in time. Light energy arrives in packets, is absorbed in stages, passed along chains of molecules, converted step by step from one form to another. The complexity of the process mirrors the complexity of the structure. Everything the tree does is layered, nested, branching, right down to the electrons moving through protein complexes in the thylakoid membrane. The DNA in each tree cell contains the complete instructions for the entire tree, including the instructions for the fractal branching pattern. But the DNA does not contain a blueprint in the way an architect's drawing contains a blueprint. It contains a recipe, a set of rules. Rules like, when a branch reaches a certain thickness, split. When light comes from this direction, grow toward it. When temperatures drop below a certain point, stop growing. From these simple rules, endlessly reapplied, the entire fractal complexity of the tree emerges. This is the beautiful secret of fractals in nature. They do not require a complex plan. They require only simple rules applied repeatedly. The complexity is not in the instructions. It is in the repetition. The tree does not need to know what it will look like when it is full grown. It only needs to know what to do next. Computer scientists have created mathematical systems called L systems, Lindenmayer systems, named after the biologist Aristide Lindenmayer, who invented them in 1968, that generate fractal tree shapes from a handful of simple rules. You start with a trunk symbol and a few replacement rules. At each branching, replace the trunk with two shorter branches at specific angles, and apply them over and over. And within a few iterations, you have something that looks astonishingly like a real tree. What this tells us is that the tree does not carry a picture of itself in its DNA. It carries a small set of rules, and those rules, played out over decades in real wind and real light and real soil, produce the tree. The tree is what the rules say when the world answers back. This is also what our own bodies are. Our DNA does not contain a picture of us. It contains developmental rules, rules that say, in the language of proteins and chemical gradients, grow here, branch there, stop when you reach this signal, start again when you receive another. And from those rules, bodies emerge, fractal bodies with branching nervous systems and branching blood vessels and branching airways, all built by the same kind of simple, repetitive logic that builds a tree. Do not miss our playlist if you're enjoying drifting through the natural world with us. There are many more quiet journeys waiting for you. You can find them all in one place. The stars above the canopy are very bright now, in the deepest part of the night. Stars are not fractals exactly, but the distribution of stars in the sky and of galaxies in the universe follows fractal-like patterns at various scales. The universe, it seems, likes clustering. Stars cluster into galaxies. Galaxies cluster into groups. Groups cluster into superclusters. And superclusters are arranged along enormous filaments separated by vast empty voids. The pattern of full and empty, of clustered and sparse, repeats from the scale of star clusters to the scale of the observable universe. When you look up through a tree at night, you are looking at two fractals at once, the branching of the tree and the clustering of the stars, framed together in the small, irregular window that the canopy makes. The near and the immeasurably far, both following some version of the same underlying logic, both branching, both repeating, both beautiful. Your breath is slow now, in, out, in, out. Each breath is itself a kind of fractal event, air entering through the nose or mouth, moving through the trachea, branching into the bronchi, branching again into bronchioles, branching again into the tiny alveoli where the gas exchange happens. Your lungs have an estimated 300 million alveoli, and their combined surface area is roughly the size of a tennis court, the same comparison we used for the oak's leaves. You and the tree are, in this dimension, the same size. Your blood vessels also branch fractally, carrying oxygen from the lungs to every cell. The total length of all the blood vessels in a human body, if you could lay them end to end, is around 100,000 kilometers, long enough to circle the Earth 2.5 times. All of that folded into a body, branching and branching, until the vessels become so fine that red blood cells must pass through them in single file, pressed between the vessel walls on both sides. Rest in that knowledge, gently. You are a branching thing at rest beneath a branching thing, both of you held by the same ancient pattern, both breathing, both held by the same quiet night. Somewhere in the forest, a small sound, not alarming. Nothing alarming will come to this forest tonight. It is the sound of an acorn falling. A single acorn, loosened by some small shift in the branch above, dropping through the layers of the canopy, glancing off a twig here, deflected by a leaf there, its fall broken and redirected by the fractal structure of the tree, so that it arrives at the ground not straight down, but at an angle, rolling a little before it settles in the leaf litter. That acorn contains, within its small, hard shell, the complete instructions for a new oak, not the instructions for a generic oak, for this particular oak, the same fractal branching pattern encoded in the same DNA that produced the tree above you, ready to be expressed again in a new body, in a new place, over a new set of decades. The acorn is patient. It does not know it is an acorn. It simply holds what it holds and waits. A single oak tree can produce tens of thousands of acorns in a good year. Most will not become trees. Some will be eaten by squirrels. who bury many of them and then forget where, thereby planting new oaks, making the squirrel one of the oak's most important partners. Some will rot. Some will germinate and be eaten as seedlings. But some, a very few, perhaps 1 in 10,000, will find the right spot at the right moment and grow. The germinating acorn's first act is to send a root downward and a shoot upward. The first branching, the first expression of the tree's fundamental direction, down into the soil, reaching for water and nutrients, up into the light, reaching for energy. From this first branching, all others follow. The seedling's first leaves, the cotyledons, are stored inside the acorn and emerge already formed, carrying the first photosynthesis the new plant will accomplish. Then the first true leaves appear, small and perfect, and begin the long conversation with the light that will last the tree's entire life. The first true leaves of an oak seedling already show the lobed, fractal margin of the adult leaf. The pattern declares itself from the very beginning. For the first few years, most of the oak's energy goes into its root system rather than its above-ground growth. If you looked at a 3-year-old oak seedling, you might think it was barely there, a thin stem with a few leaves. But below the surface, the root system is already extensive, already branching in the same fractal pattern it will follow for the rest of the tree's life. The tree is building its foundation. It is investing in what does not show yet. This patience is characteristic of long-lived trees. They invest differently from short-lived plants. They build for centuries. They do not rush toward the light the way an annual plant does, burning through its resources in a single season to produce seeds before the frost. The oak knows, in the way that processes rather than minds can know, that there will be another spring and another after that. It can afford to grow slowly, to build well, to invest in roots before branches and structure before height. The first century of an oak's life is spent becoming solid. The second century is when it truly comes into its own, wide-crowned, deeply rooted, its bark deeply furrowed, its annual acorn crop enormous. The third century begins a long, slow transition toward becoming ancient, some branches dying back, hollows forming in the trunk, the outer canopy losing some of its density, but the overall presence of the tree becoming immense, almost planetary. An ancient oak of 400 or 500 years is a different category of being from a young tree. It is closer to landscape than to plant. The dying back of branches in old trees is not a sign of illness. It is part of the tree's long strategy. Old wood and dead branches provides habitat for hole-nesting birds, for insects, for fungi. The hollow formed when a dead branch falls creates shelter for owls and bats. The tree does not simply stop being useful when parts of it die. It transforms its usefulness, trading one kind of life for another. Even a dead tree, a standing snag, teems with life. Woodpeckers excavating for insects, fungi breaking down the wood, beetles and their larvae tunneling through the soft inner wood, mosses and lichens colonizing the surface. A fallen tree continues this process on the ground. Over decades, a large fallen log becomes what ecologists call a nurse log, a long, raised platform of gradually softening wood that holds moisture and nutrients, providing the perfect substrate for seedlings. In dense rainforests, you often see lines of young trees growing in perfect rows along the remains of an ancient fallen trunk, their roots straddling the old log on either side. The old tree, in dying and falling, planted the next generation. If this gentle journey is helping you find rest tonight, a like on the video and a comment means so much to us. We love knowing you are out there, drifting through these quiet forests with us. The fractal pattern of a tree, then, extends beyond a single life. The tree that fell became the platform for the trees now growing from its remains, and those trees will one day fall and become platforms for more trees. Generation after generation, the same branching pattern expressing itself in new bodies, in new wood, in new leaves, catching new light. The forest is a fractal in time as well as space, repeating its pattern across centuries, the same way a branch repeats the pattern of the trunk. The forest around you has been a forest, in one form or another, for a very long time. The individual trees change. The species may shift with the climate. But the pattern, the branching, the cycling, the endless translation of light into wood, into soil, and back again, that pattern persists. It is older than any tree. It is older than any forest. It is the pattern the world learned to make before it had eyes to see itself with. The forest is at its most silent now, the hour before the first hint of dawn, when even nocturnal animals have found their resting places and the day animals have not yet begun to stir. The stars are at their most brilliant in this hour, undimmed by any growing light, and the fractal of the tree's branches is silhouetted against them in a kind of lacework, dark wood against bright points of light, near and far in the same frame. Mathematicians looking at trees and other natural fractals have developed ways to measure the exact complexity of a fractal pattern, a number called the fractal dimension, or Hausdorff dimension, after the mathematician Felix Hausdorff, who described it in the early 20th century. For a perfectly branching theoretical fractal, this number can be calculated precisely. For a real tree, it must be measured by taking photographs and analyzing them mathematically, counting how the branching pattern changes as you zoom in. What mathematicians have found is that the fractal dimensions of real trees cluster in a particular range, roughly between 1.8 and 2.0 for most species, and that this range corresponds to the range that humans find most pleasing and most relaxing. Below about 1.3, patterns are too simple and boring. Above about 2.3, they are too complex and agitating. Trees sit right in the middle, in the sweet spot of complexity that our nervous systems have evolved to find comfortable. This is not a coincidence. We evolved in forests. Our ancestors lived in and around trees for millions of years. The fractal complexity of a tree canopy is one of the oldest, most consistent visual environments the human eye has ever encountered. Our visual systems are calibrated for it. Our brains find rest in it. When you look at a tree and feel something soften in your chest, that is not sentiment. That is recognition. The same calibration applies to natural sounds and to natural movement. The wind in trees moves in what mathematicians call pink noise, a pattern of fluctuations where low-frequency variations are larger than high-frequency ones, producing a sound that is neither too repetitive nor too chaotic. Pink noise is found throughout nature, in heartbeats, in ocean waves, in the fluctuations of light from the sun. It is the sound of something alive and complex, but fundamentally stable. Rain falling through a forest canopy also produces pink noise, each raindrop landing on a leaf at a slightly different moment. The sound of many small impacts blending into a soft, complex roar that is somehow both uniform and endlessly varied. Rain on leaves is one of the most reliably sleep-inducing sounds humans know, because it is pink noise falling through a fractal filter modulated into something our sleeping brains recognize as the world going on safely without us. A leaf catching a raindrop does something beautiful. It bends under the weight of the drop, storing energy, and then springs back, launching the drop forward and downward in a new direction. A large leaf can redirect rain for a considerable distance. The fractal architecture of the canopy means that a single raindrop may be redirected by dozens of leaves before it reaches the ground, each leaf imparting a tiny new direction so that the drop lands far from where it began, moving water from where it is to where the roots can find it. The drops that collect on the outer surfaces of leaves and run to the leaf tip and fall as a single large drop are called drip tips, a feature especially common in tropical forest leaves, which have elongated pointed tips precisely because the jungle is so wet. The drip tip allows each leaf to shed water quickly, preventing algae and mosses from growing on the leaf surface and blocking the light the leaf needs. The shape of the leaf is designed around water just as much as around light. Tropical rainforests have the most complex fractal canopies of any forest on Earth. The multiple layers, emergent trees breaking above the main canopy, the canopy layer itself, the understory below, the shrub layer, the ground layer, create a fractal of layers, each with its own light regime and moisture level and temperature. The number of species supported by this multi-layered fractal complexity is almost incomprehensible. A single hectare of Amazon rainforest may contain 400 or more tree species alone, each with its own branching pattern and leaf shape and flowering time. The emergent trees, those that break above the main canopy and stand in full sunlight, have a different shape than the trees in the canopy below. In the canopy, the competition for light means trees grow tall and relatively narrow, reaching upward. Above the canopy, an emergent tree spreads wide, its crown opening out like an umbrella once it is no longer competing with neighbors for light. The fractal pattern of its branching shifts gears as it crosses that invisible boundary between the shade below and the open sky above. This responsiveness to conditions is one of the fractal's greatest virtues. Because the pattern is generated by simple rules applied locally at each individual branching point, the overall tree can respond to its environment at every scale simultaneously. A branch that encounters shade will grow differently than one in sun. A root that reaches a water-rich layer of soil will branch more densely there. The fractal is alive. It adapts. It is not a fixed blueprint, but a living conversation between the tree's internal rules and the world it grows in. Breathe out slowly. Let the air leave you without hurry. There is nowhere you need to go. The forest knows what to do with the night, and you know what to do with this moment. Rest. There is a very faint change in the air now. Not light yet, not even the suggestion of light, but a slight warming, a degree or two of change in the temperature that is not felt by the skin so much as sensed by the body's deep internal clock. The night is beginning its long, slow turn toward morning, imperceptibly, without announcing itself. The tree knows this. Long before the sky shows any color, before any bird wakes to sing, the tree's cells are already beginning to shift their chemistry in response to the change. Not the temperature change, which is too small to trigger growth, but the change in the electrical signals from its own internal clock, which has been tracking the length of the night and comparing it to the day with a precision that has been refined over hundreds of millions of years. This internal clock is called the circadian rhythm, and it is present in every cell of the tree simultaneously, not in a brain, which the tree does not have, but distributed across every cell of every organ, every leaf cell, every root cell, every cell in the bark and wood. All are keeping their own version of the same time, all synchronized to the same signal. The tree is not one clock, but millions of clocks, all ticking together. The signal that synchronizes them all is light, specifically the ratio of red light to far red light, which changes predictably as the day lengthens or shortens. The tree's leaves contain photoreceptor proteins called phytochromes that detect this ratio and communicate it to the rest of the tree. The phytochromes are the tree's eyes, not capable of forming images, but exquisitely sensitive to the quality of light. At dawn, the first light that reaches the forest, before the sun is even above the horizon, is rich in far red wavelengths. This early light triggers a cascade of responses in the tree's phytochromes, beginning the process of opening stomata, increasing the rate of photosynthesis-related protein synthesis, beginning the upward movement of water. The tree wakes up, slowly and completely, guided by light it cannot see with eyes it does not have. The opening of stomata at dawn is itself a beautiful process. The guard cells, pairs of sausage-shaped cells flanking each stomatal pore, change shape as they fill with water, bowing outward and opening the gap between them. When they are fully open, the pore is an oval shape just large enough for gas molecules to pass through. When they deflate, the gap closes. All day long, the guard cells mediate between the need for gas exchange and the need to conserve water, opening wider when water is plentiful and beginning to close when the tree is under stress. The regulation of stomata is another example of fractal logic operating at the cellular scale. The decision made by each pair of guard cells is local. It depends on the water pressure in that cell, the light hitting that leaf, the carbon dioxide concentration in that airspace. But the aggregate of millions of such local decisions across millions of leaves produces the tree's total gas exchange for the day, a global behavior emerging from a fractal of local choices. This is, again, the fractal principle. Complexity arising from simple local rules. No central planner, no master cell giving orders, just millions of cells each responding to what is immediately around them, and the sum of all those responses making the tree work. It is the same principle by which bird flocks form their swooping, wheeling shapes without any leader, by which ant colonies build complex tunnels without any architect, by which markets reach prices without anyone setting them. The fractal is not just a shape in nature. It is a way of organizing. We find the fractal beautiful, perhaps, because we recognize it. We are built this way too. Our own bodies are governed by this same principle of local decisions aggregating into complex behavior. Our immune cells circulate without being directed. Our neurons fire patterns without any central conductor. Our gut bacteria make decisions that affect our mood without consulting our brains. We are fractally organized, and we meet the tree's fractal organization with a recognition that feels something like belonging. The Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21, 34 appears throughout living things, and it is related to the fractal branching of trees in a subtle way. Many trees produce branches in a pattern related to these numbers. A main stem produces a branch, the main stem continues and produces another branch. The first branch and the main stem both continue, and the main stem produces a third branch, and so on, in a rhythm that produces Fibonacci numbers at each generation. The spirals of a pine cone, counting the scales in each direction, will always be consecutive Fibonacci numbers. The spirals of a pineapple, the spirals of a sunflower head. The Fibonacci sequence and the golden ratio that underlies it emerge naturally from the fractal process of growth. No plant calculates them. They are simply what happens when a growing thing adds each new part in a way that minimizes overlap with what already exists. The mathematics arrives by itself, the way dew arrives on a leaf, not placed there, but condensed from what was already present in the air. Your eyes may be very heavy now, and your breathing very slow, and the boundaries between waking and sleeping may be growing soft and indistinct. That is exactly right. Let that softness come. You are in a forest that knows what it is doing, beneath a tree that has been growing for longer than you can imagine, surrounded by a pattern that the universe has been practicing for hundreds of millions of years. You are very safe here, very held. The first bird sings before the light. A single clear note from somewhere high in the canopy, a sound so clean and simple that it seems to make the darkness more itself rather than less. The way a single lamp in a large room shows you how big the room is. The note hangs in the air for a moment, and then there is silence again. The bird is testing something, checking the dark with its voice. Birds sing from their highest available perch, the outermost tips of the tree's highest branches, so that their song carries as far as possible in every direction. By singing from the fractal's most extreme point, they maximize their reach. The tree, by providing those outermost points, enables the song. The bird song and the tree are in a relationship we might not usually notice. The tree's fractal structure is the stage on which the bird's music is performed. Different birds sing from different positions in the canopy, and researchers have found that the acoustic properties of different canopy levels shape the kinds of songs that are most effective there. Near the ground, where there are many reflective surfaces and the sound is scattered by leaves and roots and fallen logs, low-frequency songs carry better. High in the open canopy, higher frequencies travel farther. Each bird sings in the frequency range that works best in its particular niche of the fractal. Voice matched to habitat, habitat shaped by the fractal of the tree. The dawn chorus, when it arrives in full, is itself a kind of fractal. Many individual songs happening simultaneously at different pitches and rhythms, interleaving without quite overlapping, creating a complex, layered sound that is richer than any single voice, but not chaotic. Researchers have found that the timing of when different species begin singing at dawn is highly regular. Each species starts at a predictable light level, earlier species singing in lower light, so that the chorus builds gradually from the first tentative notes of thrushes to the full voice of the morning. But that chorus is still a little while away. For now, there is only the single voice in the dark, and the answering silence, and the tree holding both. Bats have been hunting all night through the canopy, navigating by echolocation, sending out pulses of high-frequency sound and listening for the echoes that return from obstacles and prey. The fractal structure of the canopy creates an enormously complex acoustic environment, full of echoes from branches and leaves and trunks at many distances. Bats that hunt in dense forest have evolved sonar systems that can distinguish a moth from a leaf in this environment, that can parse the complex fractal of sound the canopy returns and extract from it the specific echo of a single fluttering wing. Bats that hunt in more open areas over water or in open forest use different calls, longer and louder, suited to a simpler acoustic environment. The bat's sonar, like the bird's song, is calibrated to the fractal density of its particular home. Species by species, niche by niche, the fractal of the tree shapes the adaptations of everything that lives within it. The moths that bats hunt are also shaped by the fractal environment in their own way. Some moths have developed ears, tuned specifically to the frequencies that bats use for echolocation. When they detect a bat signal, they perform evasive flight maneuvers, looping and diving, that exploit the complex fractal space of the canopy, ducking between branches and behind leaves where the bat's sonar may be confused or blocked. The moth's escape strategy is to use the tree's fractal complexity as a shield. Some moths go further. They have evolved fur-like scales on their wings and bodies that absorb sound rather than reflecting it, making them acoustically invisible to some bat sonar. The texture of these scales is, you might have guessed, fractal, creating a surface that catches and dissipates sound waves across many small surfaces simultaneously. The same principle by which an anechoic chamber's foam walls absorb sound, but achieved by biology rather than engineering. Everything in the forest is in conversation with the fractal. Everything has been shaped by it and has found ways to use it. The moss on the bark, the lichen on the stone, the earthworm in the soil, the bat in the air, the moth dodging through the dark, all of them negotiating with the same branching geometry, all finding their particular way to live within it. If you are finding your eyes drifting closed and the words beginning to arrive softly, like leaves on water, you are in exactly the right place. Stay there. The rest of the story will find its way to you even so. The fractal pattern of trees has inspired artists since humans first noticed beauty in the world. Cave paintings include stylized trees. Ancient Egyptian columns were often shaped like bundles of papyrus stems, an early architectural echo of the branching plant. Japanese art developed the technique of enso, the perfect circle, partly as a counterpoint to the endlessly complex fractal of the natural world, a simple human shape resting in a fractal context. The Japanese art of bonsai is, in part, a meditation on the tree's fractal. The bonsai artist works with a single small tree, pruning and wiring its branches to express the fractal pattern of a full-sized tree in miniature, not just the shape, but the spirit. A good bonsai is not just a small tree. It is a fractal in miniature that carries the presence of something much larger. Looking at a bonsai, the mind expands toward the scale it implies. It is a portal made of wood and patience. Do check out our playlist when you have a moment. There are many gentle stories waiting there about forests and oceans and mountains and the quiet lives of small things, each one made with the same care as this one to help you find your rest. The sky, if you were to look up now, would show the faintest difference. Not color yet, but a slight loss of absolute darkness in one direction. The stars in that direction have not dimmed, but the space between them looks different. Something is changing very slowly in the east, so slowly that if you look directly at it, you cannot see it moving. You can only look away and look back and notice that it has changed. The pre-dawn quiet has its own particular quality, a stillness that is not empty but full, pressed full of the night's accumulated silence. The tree above you has been in this quiet for hours now, its branches barely moving, its cells resting in their slow night rhythms. The leaves have lost most of the dew now, or perhaps gained more. It is difficult to tell in the dark. The leaf surfaces are cool and slightly moist to the touch, the way the skin of something sleeping is slightly cool. Trees and forests are connected not only by their root networks and the fungal web beneath them, but also by the air above them. The volatile organic compounds that trees release, the phytoncides, and many other chemical signals, drift through the forest on air currents, carrying information about the state of the trees that released them. A tree that is being attacked by insects releases specific blends of volatiles that neighboring trees can detect and to which they respond by producing their own defensive chemicals. This chemical conversation happens on a slow time scale, hours and days rather than seconds, and it moves through the air in gentle, drifting plumes that expand outward from the source tree in branching paths determined by the wind. The chemical signals spread through the forest like roots through soil, reaching outward, branching with the air currents, diminishing with distance. The forest speaks to itself in chemistry, in branching plumes of scent. Some of these chemical compounds attract predatory insects, wasps, and parasitic flies that attack the insects eating the tree. The tree, by releasing these compounds, is effectively calling for help from a third party. The wasp arrives because it has been trained by evolution to follow the scent of the tree's distress call, because following that scent leads it to its prey. Tree, prey, insect, and predatory wasp are all locked in a relationship shaped over millions of years of coevolution. Coevolution is its own kind of fractal. The shape of each species is partly determined by the shapes of the other species around it, which are in turn partly determined by each other, all of them adapting to each other's adaptations in a pattern that repeats across evolutionary time, each new trait eliciting a new response, each response enabling a new trait. The ecosystem is a fractal of relationships, as well as a fractal of shapes and spaces. The fig tree and the fig wasp are perhaps the most intimate example of this coevolution. The fig fruit, which is actually a hollow ball of flowers turned inward, is pollinated exclusively by a particular species of tiny wasp. The wasp enters the fig through a small hole, pollinates the flowers inside, lays its eggs, and dies. The next generation of wasps hatch inside the fig mate, and the females emerge carrying pollen to find a new fig. Without the wasp, no figs. Without the fig, no wasp. They have been evolving together for around 80 million years. The inside of a fig, with its inward-turned flowers, is itself a kind of fractal interior. The structure turned in on itself, the surface made interior, the expected outside enclosed. It is the tree's fractal logic applied to a fruit. More surface in less space, more function in a smaller volume. The Romanesco broccoli, which is a vegetable rather than a tree, but is worth pausing on for a moment, is perhaps the most beautiful, visible fractal in the plant kingdom. Its pale green spiral towers are themselves made of spiral towers, each of which is made of smaller spiral towers, down through 4 or 5 levels of visible detail. It is an almost perfect natural realization of a mathematical fractal, and it is edible. You can eat a fractal. It tastes apparently like broccoli. The branching of rivers, seen from above, forms what are called dendritic drainage patterns. Dendritic from the Greek for tree, because the pattern looks exactly like a tree. A river basin, from above, is a tree lying on its side. The trunk is the main river flowing to the sea. The large branches are the major tributaries. The smaller branches are the minor tributaries. And the finest twigs are the smallest streams, right down to the rills that form on a hillside during heavy rain, branching as they flow downward, joining and joining, until they become a stream, and the stream becomes a river. The river and the tree are mirror images of each other in terms of what they are doing with water. The river gathers water from many small sources and delivers it to one large destination, the sea. The tree gathers water from many small root tips and delivers it to one large destination, the air, through transpiration. One collects, one disperses, and their shapes, as a consequence, are the same. The watershed of a river and the canopy of a tree are both catchments, one catching rainfall from the sky, the other intercepting it on its way down. Between them, trees and rivers manage the movement of water across entire landscapes, buffering floods and droughts, maintaining the slow, steady transfer of water from rain to soil to groundwater, to stream, to sea, to cloud, to rain again. The water cycle is a fractal cycle, from the global movement of moisture in the atmosphere down to the single molecule of water absorbed by a single root hair and breathed out through a single stoma on a single leaf. Your breath goes on, slow and even, in and out. Water vapor leaves your lungs with every breath, tiny, invisible amounts, and joins the air. Perhaps someday some of that water will fall as rain in a forest. Perhaps it already has. Perhaps you have been part of the water cycle for your whole life without knowing it, breathing the forests of ancient trees and returning the gift in your own quiet, exhaled way. The eastern sky has found its color. It is the faintest possible blue, lighter than the rest, a blue that is almost gray, almost white, a color that the eye only identifies as color by comparison with the still dark west. The tree above you has turned from a silhouette to a form. You can see the texture of the bark now, the particular way the trunk rises, the shape of the lower branches emerging from the darkness like islands rising from water. In this first pale light, the fractal of the tree is at its most softly visible. The branches emerge gradually from the dark, each one revealing itself layer by layer as the light builds. First the largest, then the medium branches, then the smaller ones, until finally the finest twigs at the canopy's edge appear as a faint, luminous haze against the brightening sky. The tree reveals itself in the same order it built itself, from the trunk out, from the large to the small. The first light of dawn is rich in blue wavelengths, the color we associate with the sky, with depth, with distance, with calm. Blue light at this intensity triggers the waking responses in the human body, alerting cells, suppressing melatonin. But at the level of dawn through a forest canopy, filtered by leaves and wood, it arrives gently, not enough to wake you if you are sleeping, but enough to deepen the quality of the sleep, to move it toward that warm, close to the surface state that borders on waking. The robin has begun to sing now, a rich, liquid series of phrases, each one slightly different from the last. The robin is one of the earliest singers in temperate woodland, its large eyes adapted to function in lower light than most other birds. By singing early, the robin occupies a quiet acoustic window before the noisier species begin, its song traveling farther through the still pre-dawn air. The robin's song is not a simple repetition. It is a series of phrases that vary in pitch, rhythm, and structure, a kind of improvised variation on a theme. Ornithologists describe it as having a fractal structure in time. Like the tree's branches, the song contains patterns at multiple time scales. Individual notes, phrases, sequences of phrases, the song as a whole. Each level has its own organization, and the levels are loosely related to each other in the same way that a branch is related to the twig and the twig to the leaf. The same singer expressing the same identity at every scale of time. Other birds are beginning to join in now. A wren, somewhere low in the undergrowth, produces a song of astonishing volume for so small a body, a rapid, cascading trill that bounces off the bark of the nearest trees and fills the pre-dawn air with urgency. A great tit, a simple, repetitive, two-note call that is exactly as confident as it sounds. A blackbird, still warm from the night, just beginning to test its voice. A few tentative notes, then silence, then a fuller phrase. The dawn chorus is building now, and it is beautiful. And if you are still awake enough to hear it, let it carry you. Let the many voices layer over each other, each one distinct, each one part of the whole. Like the branches of the tree laying their individual shadows over each other on the forest floor, a fractal of sound, complex and complete, built from simple individual voices, each one singing its own clear part. We are very glad you are here with us tonight, and if you have made it this far, please do leave a like. It means everything and costs nothing, and it tells us to keep making these quiet journeys. The light is growing now with a certainty it did not have before. Not sudden, but gathering, building, each minute noticeably brighter than the last. The tree is revealing itself fully, the colors of the bark coming back, the green of the leaves beginning to emerge from their nighttime blue-gray. The forest floor is becoming visible, the leaf litter with its 1,000 shades of brown, the moss patches their particular deep green, the stones half buried in the duff. The first direct sunlight will arrive not from above, but from the side, coming in horizontally through the trees from the east, long shafts of gold that illuminate dust motes and spores drifting in the air, that light up the undersides of leaves and the rough texture of bark in a way that noonlight never achieves. This horizontal light reveals the three-dimensional structure of the forest better than any other light does. It casts long shadows, shows the depth of bark furrows, illuminates the branching structure from the side so you can see it in relief against the deeper shadow behind. In this side-lit dawn, the fractal of the tree is at its most architectural. You can see not just the shape of the branches, but their roundness, their weight, the way smaller branches emerge from larger ones at particular angles, the way the bark wraps around each joint and thickens where the stresses are greatest. The tree is structure revealed by light, a form made visible by the accident of the sun's angle. As the sun rises, the dew that has settled overnight on every leaf surface begins to evaporate. This is not a sudden event, but a gradual one, each drop warming slowly, the outer surface of the drop evaporating first, while the center remains liquid, the drop shrinking to a smaller sphere, then a smaller one, then vanishing entirely, leaving no trace but a slightly shinier patch of leaf surface that will itself be gone in minutes. The dew gives its water back to the air the same way the tree breathes it out, by evaporation, invisibly, returning to the cycle. Let your eyes close now, if they have not already. Let the birdsong become background. Let the warmth settle over you like a hand placed gently on a shoulder. The forest is awake and singing and photosynthesizing and branching, and the whole ancient, patient, fractal world is turning steadily beneath you, and it does not need you to do anything right now except be here in this warmth, in this quiet, in this moment that is the same shape as all moments, complete in itself, branching into what comes next, held by everything that came before. The tree branches and branches and branches, and the branch becomes a twig, and the twig becomes too fine to see, and the finest twig becomes the air, and the air is full of light, and the light is warm, and the warmth is yours. Sleep well.